Bismillahirrahmanirrahim. Assalamu alaikum ji. We were talking about logistic regression, which we use to carry out classification in machine learning. Next, we will talk about two algorithms that are also used for classification. The first one is Perceptron Classifier, and the next we will talk about support vector machines. Perceptron Classifier is arguably the most elementary binary classifier in machine learning. In fact, it is a type of a neural network model, and perhaps the most simplest type of neural network model. From a conceptual point of view, understanding how perceptron classification works is often considered fundamental knowledge in machine learning. And we are studying this as we will be using these concepts to understand neural networks. The outline to study perceptron classifier would be, we will start with introduction to perceptron. How can we build a classifier using perceptron? How can we develop a learning algorithm for perceptron classifier? What is the geometric intuition of the perceptron learning algorithm? And finally, we will conclude this perceptron classifier by analyzing the convergence of perceptron learning algorithm. Okay, we will start with an overview of linear classifiers. We say the classes are linearly separable if we can have a hyperplane as a decision boundary that separates the two classes. So this is an example of the data in which the classes are linearly separable. We say that the data is not linearly separable with respect to classes if we cannot have a linear decision boundary, if we cannot fit a hyperplane separating the classes. For linearly separable data, we can have a linear classifier. A classifier would be a simple a hyperplane that is separating the classes. Here, hypothesis function is theta transpose x plus theta naught. Given our prior knowledge, I assume we have a very good understanding of this linear classifier. That this theta transpose x plus theta naught, this represents a hyperplane in the feature space. And this hyperplane is parameterized by theta and theta naught. The interpretation of theta naught is the offset, and theta represents the orientation or the slope of the classifier. My apologies. So this linear classifier, if we visualize in two-dimensional space, it's a line in 2D, it's a plane in three-dimensional space, and in higher dimensions, we call it a hyperplane. For example, if in three-dimensional space, we have a data which is linearly separable, and we have this two-dimensional plane that is separating these two classes. So we have been looking at linearly separable data for a while, and we have studied three classifiers so far. The first one was KNN, which we call instance-based algorithm. Then we talk about naive Bayes. Naive Bayes can be used for linearly separable data. Naive Bayes is generative in nature. And recently we talked about logistic regression, which is discriminative algorithm. So next, as I said earlier, we'll talk about two more discriminative classifiers, perceptron and support vector machine. We start with McCulloch-Pitts neuron. So it's a model proposed by McCulloch and Pitts back in 1943 for a biological neuron. We start with a simplified illustration of biological neuron first, and then we will talk about McCulloch-Pitts neuron. So in our brain or in our body, we have billions of neurons connected to each other, and we send the information that are sensed by our organs to the brain through these neurons. If we talk about one of those neurons, a simplified model would look like this, in which we have dendrites that serve as an input node. A neuron takes an input signal through dendrites, and these signals are combined or processed in soma, and once we have a process signal, we pass on the process signal through to other neurons or to the output node through axon. And once axon receives an output signal from the soma, it is transmitted to other neurons through synapses. So we have dendrites, soma, axon, and synapses. This might be biologically inaccurate as there is a lot more going on out there, but on a higher level, this is what is going on with a neuron in our brain. Every neuron takes an input, process it, and it gives an output. Usually we say that neuron is fired or neuron transmits a signal when it is activated by the combination of input signals. So neuron receives some input signals, it combines them and processes them, and neuron is fired or it transmits signals when we have a special combination of these input signals. Right? So this was a very simplified illustration of a biological neuron. Let's see what was proposed by McCulloch-Pitts. So we assume that we have d number of Boolean inputs. This is consistent with our notation, and we have a Boolean output, 0 and 1. So what McCulloch and Pitts proposed, that if sum of inputs is less than some parameter, some threshold theta, the output is 0 and 1 otherwise. So that was a very simplified model by McCulloch and Pitts. So you're getting signals in dendrites, input nodes. You simply aggregate the inputs, and if the sum of the inputs is less than some threshold, the output is not transmitted to the next neuron, or if the sum is above some threshold, then this threshold theta, the output is transmitted to other neurons. Mathematically, it simply means that output is 1 if the sum of the inputs is greater than or equal to theta and is 0 otherwise. So the idea is fire the neuron if at least theta number of inputs are active, because here we are assuming that inputs are Boolean and output is Boolean. Graphically, this can be represented in this form. So we have d number of inputs. This is McCulloch and Pitts neuron. It has 2 stages. The first one is it aggregates, it combines all the inputs. So this is the aggregation stage, and the next stage is thresholding. If this sum is less than theta, the output is 0. If it is greater than or equal to theta, the output is 1. Right? So theta is a parameter, is a thresholding parameter that characterizes a neuron. So, or we can say McCulloch-Pitts neuron has only one parameter, theta threshold, on the sum of number of inputs, on the sum of the inputs. Right? Okay, let's see some examples using McCulloch-Pitts neuron. So for example, we want to implement a function which is OR of 2 inputs. So we have 2 Boolean inputs and 1 Boolean output. The output is 1 if either of the input is 1. Output is 0 if both of the inputs are 0 and 1 otherwise. Mathematically, it simply means, or if you use graphical representation, we have this implementation of OR function using McCulloch-Pitts neuron. So we have 2 inputs. If the sum of 2 inputs is greater than or equal to 1, the output is 1 and is 0 otherwise. If we visualize this graphically in a 2-dimensional Boolean space, right? So these are the 4 possible inputs. Input can be 0, 0, 1, 0, 0, 1, or 1, 1. Right? And if we see this classifier, so So if sum of inputs is greater than or equal to 1, that means if we get any output or any point on this line and any point that is greater than or equal to this line. So for that point, the output is equal to 1, and if you get something here, for this, the output is 0. Right? Similarly, we can also implement AND function using McCulloch-Pitts neuron. Can you implement for me? So maybe you can pause the video and try to implement it. It's super simple. So what is AND function? If both the inputs are 1, the output is 1 and 0 otherwise. It simply means you combine inputs, you aggregate inputs, and if you set threshold equal to 2, that's AND. Right? This is the implementation of AND function using McCulloch-Pitts neuron. And graphically, so this is the boundary that is defined by this mathematical formulation, or this perceptron. Oh, sorry, it's not perceptron yet. This is a neuron. And anything on this line and here would be classified as 1, or would be assigned output 1 and a 0 otherwise. Right? We can extend this. We can have R of 3 inputs. What should be theta? This should be 1, right? If either of the inputs 1, the output is 1. Output AND of 3 inputs, in fact. This should be 3 inputs. Theta should be 3 in this case. If all 3 inputs are 1, the output is 1. So this was proposed by McCulloch and Pitts. So it's a very simplified, in fact, most simple model of biological neuron. If aggregate is greater than some threshold, the neuron is fired, otherwise the neuron is not activated. Let's talk about some of the limitations of McCulloch-Pitts neuron. Right. So it can classify if inputs are linearly separable with respect to the output. Obviously, because the decision boundary is a sum of inputs. Right? In fact, there are no weights. How to handle the function mappings that are not linearly separable? We cannot use MP neuron, McCulloch-Pitts neuron, to handle the functions, the classes that are not linearly separable. MP neuron can only handle Boolean inputs. It gives equal or no weightage to the inputs. How can we assign different weights to different inputs? How can we modify MP neuron so that we can assign different weights to different inputs? In MP neuron, we hand code threshold parameter. Can we automate the learning process of the parameter? So all of these shortcomings, or all of these questions, can be answered by modifying the model of a biological neuron, or by updating this MP neuron model. To overcome these limitations, another model known as perception model, or we call it Perceptron for short, and that was proposed by Rosenblatt in 1958. In fact, Rosenblatt developed a machine that could recognize, that could classify the letters and alphabets. So what are the good things about Perceptron? Inputs can be real valued, and we use weights while combining the inputs. Furthermore, learning of weights and threshold is possible. Let's look at perceptron in more detail. So again, we assume we have d number of real valued inputs, x1, x2, xt. But here the difference is that these inputs are real valued. For the case of MP neuron, we had Boolean inputs. Again, we assume that we have a Boolean output. If sum of inputs is less than theta, the output is 0 and 1 otherwise. This is exactly the same what we had for the case of MP neuron. Threshold, theta, and weights are model parameters. For the case of MP neuron, we only have theta as the model parameter, but here we have these weights which are model parameters. Right. So graphically, we can represent a perceptron in this form. We have d number of inputs which can be real valued. We multiply each input with different weight. So x1 with w1, x2 with w2, and then we aggregate here, and simply aggregation is simply followed by thresholding. Right? So on this side we have MP neuron. We have introduced these weights here, and we have allowed these inputs to be real valued. This is the only difference. So these are the two differences from MP neuron. Mathematically, output would be simply given by that output is 1. Again, when weighted sum is greater than or equal to theta is 0 otherwise. So theta is a threshold parameter. In fact, that represents a bias here. Theta can be considered or absorbed as a weight. This will simply make aggregation thresholding independent of any parameters. We did the same while studying logistic regression, that we absorbed the threshold, we absorbed the bias. We considered the bias as a weight. It simply means if you move this theta to the left hand side in these equations, so now our threshold is 0, and we are considering theta as a weight to the input, or weight to the one input, weight to the constant input that stays 1 all the time, right? Graphically, this can be shown in this form. I have introduced an additional input here. I'm calling it x0, right? But that is constant input. So this is not coming from the feature space. This is not a feature, but this is a constant input. And for this constant input, I have introduced a weight minus theta, and I will use w0 to denote minus theta. And mathematically, we have a standard perceptron model. Right, threshold is 0 here, or we can say threshold has been absorbed as a model weight. Right? It's an alternative representation, or mostly used representation, and we will encounter this while studying neural networks. An alternative, more compact representation is also followed in the literature, and we will also use from this point onwards. That we can write these weights instead of as a separate block on top of these input arrows. We have x0, x1, x2, xd. So d features, one constant input minus theta is the weight associated with the constant input. And for the rest of the d inputs, we have w1, w2, wd. If I use x to denote, if we use vector x to represent d plus 1 inputs, and w to represent d plus 1 weights, I can write this aggregation, what proposed here, as a simply inner product between w and x, or simply w transpose x. We can also write this as in this form. If inner product is greater than or equal to 0, the output is 1. If inner product is less than 0, the output is 0. Right? So this is a mathematical model of a perceptron, or in fact perceptron classifier. How do you interpret this? If the weighted sum of the inputs is greater than some threshold, the output is 1. If weighted sum of inputs is less than the threshold, the output is 0. Right? Or we can say we have a linear decision boundary that is separating the two classes 1 and 0. We assume that we know the weights W that are characterizing my perceptron, and if we have these weights, how can we use this perceptron model or perceptron classifier to carry out classification? If you see, we have this decision boundary, W transpose X is equal to 0. And our prior knowledge informs us that this represents a hyperplane in the D-dimensional space. And we can use this as a binding classifier if the classes are linearly separable. This is different from empty neuron. Inputs are real valued. We have real valued weights in the process of aggregation, and we will see very shortly that we can learn these weights. In fact, we have seen this before, right? If you connect this with the logistic regression, in logistic regression, we use the same weighted sum of the inputs plus bias, and then we pass this weighted sum through sigmoid, right? Because we want to squeeze from minus infinity to infinity to 0 and 1, right? So that was logistic regression. Or we can say a perceptron classifier is a subset of logistic regression model. If I, instead of having this thresholding stage, if I replace thresholding with sigmoid, what I get is perceptron, right? There's a debate whether we should teach perceptron first, or whether should we cover logistic regression first. Since we were studying regression before logistic regression, it's always natural to study logistic regression and make a connection with the regression. And now we know logistic regression, it's very easy to follow this simple perceptron classifier. Right. So we have seen this before. Perceptron classifier is exactly the same output what we had for the case of logistic regression. And due to this, the logistic regression classifier is referred to as an elementary neural network. So perceptron is the simplest neural network, right? So logistic regression is also referred to as an elementary neural network. I have explained this. And the question is, how can we learn the weights for the case of perceptron? Due to thresholding, due to non-differentiability of the final decision, right? So we have a thresholding here, right? If we have a weighted sum greater than 0, output is 1. Weighted sum less than 0, output is 0. So this is not differentiable function. So we cannot use gradient descent. So we will, in the next video, we will talk about a perceptron learning algorithm, which we can use to learn these weights given linearly separable data. Before we conclude, I would like to just note one more point. If we label the classes as 1 and -1, so only this decision would change. So if W transpose X is greater than 0, we get 1. If W transpose X is less than 0, we get -1. This can be compactly written as in this form. If we use this sign W transpose X, right? So we are simply assigning the sign of W transpose X to y. If W transpose X is negative, we use -1. If W transpose X is non-negative, we use 1. Right? So sign simply returns sign of the argument. So now we have a good understanding of perceptron classifier that simply represents a hyperplane in the d-dimensional space. This hyperplane is parameterized by this vector w. Right? If you get a test point, you simply take an inner product with w. If that inner product is non-negative, output is 1. If inner product is negative, output is 0. That's a simple classifier, perceptron classifier. Right? We stop here. In the next video, we will talk about perceptron learning algorithm.